Welcome to the Beyond tutorial on estimations and approximations. Last week we looked at estimating when we know some related quantity, when we can estimate about some related quantity, how to systematically build that relation to this unknown, systematically going from known to unknown. Okay, this week we will look at slightly more complex problems where we cannot even figure out something known about the given problem. So how do we solve that? Let's say the question here is, I want to guess the weight of a mid-sized car that just started a long drive with a family. Now, what can I relate this to? Is there something that I know if I can compute, then I can compute this? I am unable to think of any factor. Last week when I wanted to figure out how many mechanics are there in Moscow, I said, okay, I will figure out what is the population of Moscow. How do I do that? Because I know the population of a South Indian city, I can sort of multiply there. But here I don't know the weight of an auto or weight of a cycle. Everything requires a lot more computation. So I now have to use a slightly different technique. This is called splitting the complex into simple. So now first step I use is, what are the components that give a weight to a car? The first thing, people. I said the car is starting a long journey with a family. Now I am assuming in nowadays it's common to have family sizes of 4 or 5, so I assume the family size is 4, and I assume the adult's father probably is 70 kgs. I'll do the computation in kgs. Mother 60, and the kids 30 each. So I know 70, 60, 30 plus 60, 130 plus 60, 190 kgs. People actually, this is one component that gives weight to the car, and that is people, and that's around 190 kgs. Now let's look at what else. Fuel. Yeah, this family started a long journey, so they must have filled their tank, and a typical mid-sized car carries with it 50 liters of fuel, 50 liters of petrol. So I would assume that the fuel costs, fuel weight 50 kgs, 50 liters, as gas or fuel actually floats on water, as petrol floats on water, I would assume the weight to be approximately equal to water, and 50 liters of water weighs 50 kgs. So the weight here contributed by the fuel is 50 kgs. Great. Now let me look at what else. Luggage. This family is going on a long drive on long drive, and hence they must be packing stuff. Normally, how heavy is a suitcase? 25 kgs, 20 to 25 kgs. So I would assume that as the family has 4 members, whether they're kids or adults, lots of stuff to pack, and hence I would assume that the luggage is a total of 4 members. Each member must be carrying around 25, so 100 kgs. Good. So the easier parts are being taken care. Now let me actually get into the tougher part, the body and the engine. So this is obviously going to be more complex than the rest of them. So let me first look at the engine part before coming down to the car other parts. There is a regular car. I would assume that I would assume that in a car of dimensions like this part has a lot of weight. It's actually filled metallic. I can assume it to be a filled metallic block. And what is the let's look at what is the length, height. There are tires here. So typically I wouldn't expect this to be any more than 2 feet. That is the height, or 0.6 meters. And width, I am expecting it to be around 1 meter, and length again 1 meter. This is from a front view I am talking about. This is how the car is, and there is this metallic thing, and then there are tires. So I'm talking about this metallic block. This is 0.6 meters and 1 meter and 1 meters. So this major contributor to the weight of a car is this volume. 1 times 1 times 0.6. This is 0.6 meter cube. How to estimate the weight? Now this is steel, this is proper metal. I estimate it to be, it sinks in water, so I estimate it to be twice as heavy as water. Okay, which is not too bad an assumption. So I would, this works out to be around 600 kgs. 0.6 meter cube, and 0.6 meter cube. 1 meter cube is around 1000 kgs. 0.6 meter cube is 600 kgs if it was water, and I would expect this to be 2 or 2.5 times heavier than that, which boils down to around 1200 to 1500 kgs. Again, I am going in a very systematic way, splitting the complex into simple. Now, what else is there? Tires float on water. How much a tire normally? I'd say it's 1 feet or 0.3 meters radius, pi r square. So 0.09 pi. That is the thing. Pi, if I approximate it to be 3, it is 0.27 meters square, and height 0.1 meters. So my volume is 0.027, but most of it is empty. Only 10% of this actually is filled, because most of the tire is empty. So if I look at the front view of a tire, I have a cylinder where most of the middle is empty. I am taking this height to be around 10 centimeters and this to be around 1 feet or 30 centimeters. And then my pi r square times this is the volume, but most of it is empty. So I'm not adding 0.027 meters. Okay, and meter cube, and I have 5 tires like that, because I'm going on a travel, 4 of them for driving and 1 as a backup. So I'm talking about 0.0135. A meter cube is 1000 kgs. So this one is 1000 times this, 10, 100, 1000. So it doesn't really add 13, 14 kgs. Let's say tires are 15 kgs. Now, obviously, this is the biggest weight, and then I have the rest of the body with some seats and other things. Rest of the body, again, I can assume it to be, most of it is empty, because there are seats and people sit, so most of it is empty. So I could take it to be 1/10 of this weight, most of it. So it adds another probably 1/5, some 200 or 300 kgs. Okay, I could actually compute what exactly the way I can actually now split it into 2 parts here. Try to measure this weight, taking the empty space and than this weight, but you got the point. So now what will be my estimate? Yeah, the body will be 1200 to 1500, let me say 1350. The rest of the thing is 1/5 of this, so around 300, 1650, and around 200 kgs from people, around 50 kgs from fuel, around 100 kgs from luggage, and around 15 kgs from tires. I can even ignore this. 1650, 1850, 1900, 2000. So a car of this size with a family that just started its journey will be approximately 2000 kilograms. This is wonderful. If you look at it, this adds a completely new technique in our arsenal. So essentially, I have split something fairly complex into simple components that I can estimate. A car that started its journey, I split it into its body, its engine, its tires, its luggage, fuel, people, and then estimated each one. So this technique is different from what we used last week. Last week we said, let me figure out what is the closest thing that I know about it and then go step by step. Most of the times, for most of the estimations that you do, you don't have that luxury. You don't know something that is you don't know the answer of something that is very close to what you're looking for. Then what you have to do is you have to first split it into multiple simpler parts and then use last week's technique, where for each one you now find what you know and then extrapolate there. So this is another extremely powerful estimation technique. So you can now start estimating what is the weight of a fully loaded Boeing 777, something as complex as that, or what is the weight of a building. All these things, you just now split it into multiple components. Again, it has all the advantages of the systematic process. If you actually, you may not find the total value, total estimation in many cases, but the individual ones you will actually be able to find enough resources that provide you the weights and other things of individual resources. Deliberately I didn't go to internet to check for the weights, but clearly you can actually fuel, engine, these things you can actually verify in the web, how much steel weighs more than water, etc., and come up with very good accuracy. So a systematic estimation always allows you to correct for update your estimates. Okay, next week we will look at one more technique of systematic assessment. Thank you very much.